Lunar landslides are relatively common, and they are caused by several sources. The lunar surface is covered in a layer of loose, highly unconsolidated dust and rock fragments. The material is extremely sensitive to vibrations and easily breaks loose. In addition to moonquakes, micrometeoroid impacts can dislodge granular flow. Through the use of high-resolution images from NASA's Moon Trek, we move to Kepler crater. Kepler displays a ray system that extends for over 300 kilometers. As we zoom down, you can see the crater's slightly polygonal shape. Kepler's diameter is 32 kilometers, and it is 2.6 kilometers deep. The crater's slumped and terraced inner walls descend to an uneven floor, and it has an off-center central peak. Notice on the far wall a landslide of dark material. The landslide begins about 100 meters below the rim from a narrow box canyon. The mid-slope portion consists of a series of narrow landslides, 20 to 30 meters wide. Notice how the individual slides overrun each other, forming a band about 180 meters wide. At the base of the slope, the individual slides can be recognized as they move apart, forming a fan of material. The terminations of the slides are formed by many boulders that are a few meters in diameter. A little further out in the boulder field, you can see evidence where this boulder bounced and rolled down the slope to its final location. Now we move east to Rima Hyginus. It is a graben formed by volcanic activity on the Moon when two parallel faults pulled apart. Notice these rimless craters, which formed when shallow underground lava pits collapsed. The largest of these pits is designated Crater Hyginus. Switching to the Chang'e 2CCD orthomosaic layer, we zoom down to the western section of the graben. Notice here where bright, boulder-rich material from the edge of the rill slid down the wall, possibly during a period of tectonic shaking due to a moonquake or forces associated with a nearby impact. The brighter rock slide material is clearly visible, along with multiple boulder tracks. A trio of large boulders also left trails as they tumbled down the rill's wall. On the opposite wall of the graben from the trio of boulders is another boulder trail. Notice how it bounced and rolled down the slope, then collapsed into a pile of rubble. We now move eastward to La Pérouse A. It is a geologically fresh, young crater known for its striking impact melt features and a bright ray system. When the impact excavated material from the side of a hill of highland material, the slope became unstable and collapsed into the crater. The landslide material inside the rim has a high reflectance, while the undisturbed section of the highland material is relatively darker. The red dashed line shows the location of the original crater rim, while the blue dashed line shows the new rim due to the landslide. We now move to the opposite limb, to a crater designated Riccioli CA. The CA designation comes from the namesake crater, and its satellite crater C contains a large impact crater with the A designation. This bowl-shaped crater has a diameter of 16 kilometers and a depth of 3,023 meters. Notice this dry flow of boulders down the slope of the crater's inner wall. The stream of bright material is made up of blocks, boulders, and smaller rocks. This conglomeration of granular material slid down the 34-degree slope towards the crater floor. It is interesting how the physics of wet material, known as Newtonian flow, in some cases applies to dry material. This slide was formed without the involvement of water. We now move to the northeastern edge of the Sea of Crises, to a crater designated Imart A. This feature is a relatively fresh impact crater, which displays some impact melt flow along a portion of its rim. Captured in striking detail by the Lunar Reconnaissance orbiter, Imart A is famous for its steep walls and dramatic asymmetric landslides and rootless impact melt. We now move to the western edge of the Sea of Tranquility, to Dionysius Crater. The crater has a diameter of 18 kilometers and has an exceptionally bright albedo. The eastern wall features dark, high-iron basaltic material, while the western wall exposes the brighter, low-iron highland materials. Seen here is a high albedo granular flow traveling down the inner wall of Dionysius Crater. At the base of that flow is a mound of impact melt that is blocking the granular flows, causing it to detour around the mound. In this beautiful image, you can see bright talus trails that wind down slope, through crags and crannies in the dark mare layers. As we zoom further out, you can see the landslide that drops some 1,600 meters down the slope. We zoom in to the distinct banded layers on the inner eastern wall. These dark-toned striations are exposed lunar basalt which were violently disturbed and uplifted by the impact, showing the region's ancient history of overlapping fluid lava flows. We now incrementally pan down the landslide, showing the beautiful interactions of the dust flow, growing into wider landslides, and eventually into a boulder field at the base. Lastly, we look at Tycho Crater, 85 kilometers wide and 4.7 kilometers deep. This massive rebound peak formed within tens of seconds during a large impact on the surface. It consists of rock brought up from deep within the Moon's interior. Tycho's central peak rises 2,000 meters above the crater floor. Multiple landslides and boulder talus can be seen on the slopes of the peak structure. Such a beautiful and dynamic vista. This is truly magnificent desolation. The central peak rose up through a massive pool of impact melt. You can see an armor plating of cooled melt on the upper reaches of the peak. Notice the 120-meter wide boulder on the summit. It may one day roll to the crater floor as the peak continues to degrade. What a sight that would be!